Okay, this is our fall 2014 AP Calculus prep session, and I'm handling problems relating F prime, and F double prime, which is really, studies have shown, the most tested topic in the AB Calculus AP test. Anyway, and besides the topic itself, it's so important a concept because it ties into so many other things that are tested. So let's go ahead and look at the concept. We have to consider a function at basically three levels. First of all, there would be an amount, a number of gallons, penguins, bacteria, etc. Then there would be a rate of change. So rate of change is going to be second level. And another possibility, an amount would be a position or distance, and the rate of change of position is velocity, which is the second level. So I'm going to call this level here second level, first. Let's see, yeah, first. I think that's show up. Okay, and then the third level is the rate of change of the rate of change. Of rate of change. I'll just put ROC for rate of change. And with regard to position, velocity, the rate of change of the rate of change is called acceleration. And so in calculus language, we would call this first level one, we would call it original function. I'll call it original function. And then the second level is going to be called the first derivative. So we take the derivative of our original function, we get the first derivative, and then the level 3 is called the second derivative. And in calculus, what we do is we are given a situation at one of these three levels, and we are asked to do some analysis to get from one level to move up or down depending on where we're going. And there are key words that we're going to examine. We're going to have parts 1 through 5 in this. The first thing we're going to look at in part 1 is the calculator portion of problems with F prime, and F double prime. There are four problems we're looking at. One thing to keep in mind is that in the calculator portion of your AP test, not all those problems, probably maybe half of the problems will be ones where you're actually going to need to use the calculator. And we'll see that here. Problem 1, the graph of the function y equals x cubed minus 6x squared plus 7x minus 2 sine x changes concavity at x equals. And we go back here, concavity is a third level type of issue. So I'm going to put down concavity. Okay, let's go ahead and look at that. And what we have is we're trying to find where this function changes concavity. So this function here resides, this is the position function. It's y equals, not y prime, is the position function. So for changing concavity, we would look at, that's a level 3 issue. That would be related to a second derivative. So let's go ahead and look at where we go with this. If we graph in our calculator this function, this is what we see. This is the function graph, the original function. And what we have is we have from negative infinity to some point around here, we have a concave down situation. So the function's concave down because it's kind of a frowny face, and then at some certain point, the function becomes concave up. And so right here, right around here someplace, there's a change in concavity, where we go from a frowny face on the left side to a smiley face, an upturn. So we're going to do an analysis to take care of that. The first thing we're going to do is take the first derivative of this thing here. So that's going to be y prime is equal to 3x squared minus 12x plus 7 and minus, well, we take the derivative of a sine, that does not change the sign, but we're going to have minus 2 cosine x. Now this is definitely a calculator problem because we have all these decimal numbers look like irrational numbers, and we're not going to be able to access any one of these numbers from here unless we use some kind of a calculator to do that or have a table. And so here we are with the first derivative graph. And the first derivative, the concavity, changes where the slope of the derivative changes from negative. So we have slope, if we drew a number line here, and we have some point here, we don't know what it is yet. Oh, by the way, we know it can't be, we're not going to have 2 points, so we can eliminate choices A and B because there's only one place that the slope of, we change concavity, I'm going to put to change concavity where the slope of y prime goes from negative to positive, POS, or from positive to negative. Therefore, we see this point here. We don't know what it is, and if we, let's say this is at, we'll call it C. We know to the left, let's say this function here is y prime, and down here is y. To the left of this value C, the slope of that function is negative, so the function is decreasing, which we amply see here, the negative slope. And to the right of C, we have a positive slope, so the function is increasing. So that's kind of what this function looks like at a first level, at the second level, the position level that we saw earlier here. And this is the position, this is the velocity level or first derivative level. Next, one thing we can do is we can take on our calculator and find a minimum. Okay, the minimum of the function, and we find our calculator by we go to, on our TI-84 calculator, we go to second, and the key we look for is the trace key, second trace, which above it has calc. And then I think, choice, looking at my calculator here, second trace, we have to find the minimum is option 3. Option 3. Minimum. And we say set left, set right. And so based on what we see here, this thing looks an awful lot like answer C, doesn't it? Let's go ahead and take another level. If we take the second derivative, and here's the second derivative, that's the first derivative work. That's okay. The second derivative, we have a sign change here. The 7 goes away, and the second derivative graph is this one right here. And our change of concavity at this is the third level, is where y double prime changes from negative to positive, or from positive to negative. All right, and we see that we're changing from negative to positive right here. So that's going to be a change in concavity. And specifically, what we have is we have, at this point again, C, if we look at y double prime and y, to the left, we have concave down, the left of C, and to the right of C, we have concave up. So that would be our change in concavity. Okay, next. Doing the analysis in our calculator, in this case we go to second, trace, and what we're trying to find is option number 2. Option 2, you write that a little better. Second trace, option 2, which is 0. And we'll find this 0. So again, it looks like C is our correct answer. Okay, problem 2. The graph of H prime is shown below. Select the true statement or statements below for function H. Okay, again, H prime. This is going to be level 2. H is level 1. H prime is level 2. And H double prime will be level 3. So we need to make this analysis, and we're asked different things, 1, 2, and 3. We're trying to find out. Well, first option is H is decreasing the interval from -4 to 2. Well, if we draw, this is going to be H prime above this red line, H below, and we don't have any critical numbers because the graphic function does not touch the x-axis or cross through the x-axis in any place. And in fact, H prime is above the x-axis at every place seen. So for all the intervals shown, we have H prime is positive. So the function is always going to be increasing over the entire interval. So H is not decreasing at all. So 1 does not work. Okay. 2. H has an inflection point at x equals -3. Well, if H prime, the slope of H prime changes from negative to positive at x equals -3, so definitely option 2 is part of the deal. 3. H is concave down in the interval -3 to 2. Well, let's go ahead and change out our number line. Instead of making it H above that, we're going to have H double prime. I'm going to erase this below. And erase this above. Basically, our change in concavity is going to occur here at -3 and also at 2. And no, that's a 2, and I forgot one more. Looks like right here at about -1 also. So to the left of 3, the slope of H prime is negative, so we are going to be concave down. And between -3 and approximately -1 or so, or -1/2, whatever that is, the slope of h prime is positive, so we're going to have concave up. And then between -1 and 2, we're going to have slope of h prime is negative, so we have concave down. And to the right of x equals 2, concave up. So option 3, h is concave down in the interval -3 to 2. Well, the function's concave down between about -1 and 2, but not all the way between -3 and 2. So 3 is not correct. Our only possible answer is B, 2 only. Okay, next problem. The graphs of the derivatives of functions f, g, and h are shown below. Which of the functions f, g, or h have a relative minimum on the open interval x is between a and b? Well, we can draw little mini number lines below these three situations. Again, this is prime. We look for our critical numbers, which are where the function will touch where f prime of x is 0. So it looks like we have a critical number here at about -1.5 and also at 1. So about -1/2 I'll put down here, and then at x equals 1. And we'll put f prime above, f below. And what's happening is to the left, we are positive. F prime is above, so the function is increasing up to I said -1/2. That's about actually -1 and -1 1/2. Graph's a little hard to read. -1 and 1/2. That's what it is. Next, between -1 and 1/2 and 1, the function f prime is below the x-axis, so the function is decreasing in this interval. And to the right of 1, function's increasing. And so a relative minimum on the open interval, well, we do have a relative minimum where f prime of x changes from negative to positive. And we can graphically kind of see that if we can connect this, we see a minimum right here. So definitely we have to include this one f. Let's look at g. Okay, where are critical numbers? Right here. Looks like at -3 is a critical number because the function touches the x-axis. -1. And this one here is going to be about 3.5. Okay, again, we're going to be talking about g prime. G prime is positive. Function's increasing to the left of 3. Function is below the x-axis over the next interval. It's going down. And then between 1, let's say -1, this is supposed to be positive. Between 1 and 3.5, function is above the x-axis. And to the right of 3.5, negative. And so, again, we see as the function changes from negative to positive, I mean f prime changes from negative to positive, this function g also has a relative minimum. And then the last one, we go from, looks like we have just a little less than 3. We'll call this -3, a little less than -3. That's a critical number. And then about here, looks like about 2.5. And this is going to be h prime and h. Now to the left of -3, we have negative. So the function is going down. To the right of of -3, we are above the x-axis, so positive, and to the right of 2.5, we're back below the x-axis, negative. So our relative minimum is found right here around x equals -3. So in this case, each one of these graphs of f prime, g prime, and h prime gives us evidence to show that the functions f, g, and h each has a relative minimum on this open interval. Okay, you may have noticed that problems 2 and 3 didn't have need for a calculator at all. Now we're to problem 4. Function f has a first derivative given by f prime of x equals a square root of x over 1 plus 2x plus x cubed. What is the x-coordinate of the inflection point of the graph of f? Again, this is going to be a second level view, which is a first derivative. And when we look for inflection point, that has to do with concavity. So we're going to go down and look at the third level. And the third level is going to be the derivative of f prime. Now, I don't know what you think, but this looks like this is going to be pretty tough taking a deriving. If we had this expression in the denominator and the numerator, and this expression in the numerator and denominator, we'd be able to simplify and work out a second derivative quite easily, but this is tough to do. But fortunately, we can use our analysis of the graphs to do this. Basically, if we find the inflection point where the slope of this guy here, f prime of x, changes from negative to positive or from positive to negative. And so the first thing I recommend is putting this function right here in your graphing calculator. Now we press the y equals key to make the graph, but to make this fraction, I want to show you the keystrokes to form the fraction. What you do is once you get in this mode where you have the functions listed y1 through y10, you press alpha and then the y equals key in the top, and then you just press enter, and then you can enter square root of x over 1 plus 2x plus x cubed, just like we have here. So we've entered that. Next, when we graph the function, this is what we see. We see barely anything at all. Right around the origin, we see this little blip right here. So definitely, we can't really see what's going on for an inflection point. So the next thing we're going to do is we're going to use zoom box. Well, zoom is your middle, it's your middle function key at the very top near the screen, and option 1 is zoom box. What you do is you get to this view here, press enter, and you move the cursor to the left and to the right, and you zoom in on this area. So what you've done is you've taken this area right here, and you've really zoomed in on a very small window of it. So you've drawn a box around this so you can really get a close view on what's going on right here. So now going back, this is what it looks like, and when the slope of f prime of x changes, in this case from positive to negative, that's going to be our inflection point right here. And to analyze that, we can go in our calculator, we can go second, trace, and I'm going to see what that is. Option 4, which is maximum. And then for that, we would get our inflection point is going to be here, answer A. So that's really this whole section here. Again, of the 4 problems, only 2 of them were legitimately real calculator problems. I hope you can see the relationship going to different levels to understand what's going on here. Thanks for viewing.